Hi, so today we're going to be looking at a problem on statistical physics. And what we have today is, we have some gas which has some fixed volume, some number of particles n, and energy E. So all of these quantities are fixed, and what this means is that we have some kind of box, right? Just notice that I'm not drawing a rectangular box because really we don't care about the shape of this box. We only care that it has volume V. Okay, so this volume is constant because the gas is inside it, it cannot go out. It's always inside this volume V, and it occupies the whole volume of the box. Also, we are assuming that the number of particles is constant, that is, particles don't go out on or in the box, and the energy is also constant. This means that there's no exchange of energy with the medium and the box. This is an isolated system. And with these three assumptions, right, constant volume, number of particles, and energy, we are in position to use the Microcanonical Ensemble to solve this problem. And before we continue, there's one more thing that we are told about this gas, and that is that we have ultrarelativistic particles. And we'll see afterwards when we solve the problem, but just really quickly, ultrarelativistic particles just means that the particles don't have mass and they can move at the speed of light. So we'll see this afterwards. Now, before we get on to the actual problem, let's do a quick recap on the Microcanonical Ensemble. I'll just go over some basic concepts that we will need in order to solve the problem, but I won't get into too much detail because otherwise the video will get too long. So, well, first of all, we need to find our phase space, and our phase space is the set of all possible states of our system. And a state of our system is described by this point, right? This point is called a state, or a microstate of our system. And what this point means is that, well, we have this first coordinate is Q, which is denoting all the positions of all the particles. That is, this Q is shorthand for really the position of the particle 1, position of particle 2, and so on until particle n. Notice that I've written Q instead of the usual R vector because we are assuming that we are in some general coordinate system, so we don't necessarily need to be in Cartesian coordinates. So Q are just the coordinates of our particles in some arbitrary coordinate system. And P denotes the momentum of each particle. So just like before, this P is just shorthand for the momentum of all of the particles. So this phase space, gamma, is composed of all the possible positions and momenta of the particles, and we can kind of divide it into two spaces: the position space, gamma q, and the momentum space. And we'll understand this better when we solve this integral, and you'll see how all of this works. Now, what is this? This right here is what's called the volume of the phase space. And it is the fundamental quantity that we need to find in order to use our Microcanonical Ensemble. Notice that in terms of this phi, which is the volume, as I said, of the phase state, we can find the entropy, which is really our goal. And after finding entropy, we can find the temperature, the pressure, the heat capacity at constant volume, and at constant pressure, and also the ratio between these heat capacities. So, in order to solve the problem, all we have to do really is to compute this integral. And we'll see now that what all of this means. And, well, and just really quickly, also, why this is called the volume of our phase space is because imagine that we are in some current system with a lot of dimensions, right? In this case would be 6 n dimensions, we will see afterwards. And we have some region right here. And all of this could be the set of all points in this high-dimensional space. This high-dimensional space, we have some region, and inside this region, the volume is the set of all points that that our system can be in. That is, all the points in this volume are the possible states QP of our system. So we are adding up all these states. Now, before we go into the integral, what is this factor here? This 1 over n factorial is what's called the Gibbs factor. We include it by hand, really, and what we mean by including it by hand is that sometimes we choose to include it or to not include it. The general rule is that when we have undistinguishable particles, we have to include it in order to not count particles more than one time. As we will see in some theory videos that I will be making, we'll see where this factor comes. Also, the h right here, this is Planck's constant, and it's just there to make dimensions correct, because we want this volume to be dimensionless, really. And what else? Yes, notice, I don't know if you can see it there, but this is h raised to this, and this is just the number of degrees of freedom of our system. What do we mean by degrees of freedom? Well, just imagine that we have a system of one particle. What do we need to define this particle, or to find this particle? We need three coordinates. We need Q1, Q2, and Q3. So we have 3 degrees of freedom for one particle. If we have two particles, we will need, well, these 3 coordinates for the first particle and another 3 coordinates for the second one. So we will have 6 degrees of freedom. And in our case, we have n particles. So really what we have is 3 degrees of freedom per particle, but we have n particles, so our degrees of freedom really are just 3n. Okay? So this is what we mean by degrees of freedom. It will not always be 3n, but generally for a gas in which we consider particles to be separated and not interacting with each other, we can assume that the degrees of freedom of our system is 3n. And what else? Well, now we have talked about this. This integral right here is the integral over the phase space. Okay, so we'll see later on how to do it. But let's just go on to the function that we're integrating. Really, this function is a really famous function. It can be thought of as a distribution. But, well, it is just the Heaviside step function. And in our case, it depends on E minus H, where H is the Hamiltonian of our system. And it is 1 when the inside of this function, right, where the variable is greater or equal than 0, and it is 0 when it is less than 0. So really we're not integrating a function that is too hard, as we'll see later on, but we do have to do the integration. And this dq and this dp, just like q stands for all of this, our dq is a shorthand notation for dq1, dq2, so on, dqn. And really, remember from vector analysis or vector calculus that this is in turn shorthand notation for this q1, q2, q3, 1, 1, 1. What does this mean? This means that this vector differential right here is the product of the differential of our first component of our first particle, the differential of the second component of the first particle, and the differential of the third component of our first particle. So really, what we have here is n vector differentials, and each vector differential has 3 terms, so really we have 3n differentials. But there is another dp, which also has 3n terms, so really, this dq, dp are 6n differential. So we are actually doing a 6n dimensional integral. It seems scary at first and kind of ridiculous, but we'll see that it is actually nicely done. And we can do it nicely because we have this relation right here, which I will not be proving in this video, but I am thinking of making a series of videos in which we prove all the integrals that we will be using in these statistical physics exercises or course. This is really interesting. We'll see afterwards how to get to use it. But well, yeah, I think that this is everything that I wanted to talk about. Well, no, let me just comment about the entropy. The entropy, well, is the fundamental quantity that we want to find. And just remember that it is extensive. And what we mean by extensive is that, well, let's say that we put it in terms of E, V, and N. If it is extensive, if we put some parameter here, lambda, then the entropy has this property. Sorry. Okay? This lambda comes out. Okay? So if we scale every variable of our function, of our entropy, we will get this relation. Now, there are other extensive quantities such as the energy, number of particles, and the volume. And there are also intensive quantities, which, well, if we put a lambda here, we actually just get the same function. There's no lambda in front of it. And this is what are called intensive quantities. In our case, T and P are intensive. We'll see later on why it's convenient to remember which quantities are extensive and intensive, because that way we can check our results. And now, this equation right here, this formula, is the Stirling approximation formula. And just tells us that if n is sufficiently large, we get that the natural log of n factorial can be approximated to a good extent by n log n minus n. And this actually simplifies a lot our expression for the entropy in many cases. And it is justified in statistical physics because what we want to do with statistical physics is to go from some classical quantum laws and try to construct thermodynamics. And in thermodynamics, what we have is a large number of particles. So this approximation of n greater than 1, a lot greater than 1, is what's called the thermodynamic limit. And it is properly justified in our purposes. And now, well, as I said before, these are some fundamental thermodynamic relations which we will use to calculate different quantities. So, well, let's just get on with the program. As I said, the first thing that we need to do is to find the volume of our phase space. So, we want to calculate this. And, well, let me just write 1 over n factorial and h raised to the number of degrees of freedom of our system. As we said before, we have n particles, and each particle has 3 degrees of freedom, so we have 3n degrees of freedom. So we will just write 3n right here. Now, we have the integral of our phase space of the Heaviside step function of our energy, which is constant, remember, minus our Hamiltonian dq dp. We need to find what a Hamiltonian is of the system. We're not given the Hamiltonian in this problem, but it's not too hard to find it. First of all, we know that our particles are confined in this box with volume V. So we will define some potential function for each particle, which will be positive infinity. If Ri is not in this volume, okay, let me just call this region of space cursor V, and it is 0 if it is inside this volume. So what this potential means is just that the potential outside the box is infinite, that is, the particles cannot be outside the box. And it is 0 inside the box, which just means that inside the box we only care about the velocity of the particles. So this would be our potential energy, and we know that particles also have kinetic energy. So the kinetic energy will be given by, well, we know already that particles have this, right? But in this case, this expression would be wrong because we are dealing with ultrarelativistic particles, as I said. So when we're dealing with ultrarelativistic particles, we no longer have this relation, but this other relation, where c is the speed of light, and this pi is the momentum of the particle. So we're taking the modulus of the momentum. So this would be our expression. Then, our Hamiltonian, which for our purposes in statistical physics represents the energy. There's sometimes some cases in which the Hamiltonian doesn't exactly represent the energy, but we'll talk about that in some classical mechanics courses. So, well, just forget about that, but just remember that the Hamiltonian, which is given in terms of Q and P, represents the energy of our system. So we have n particles, so we have to add the energies of n particles. And, well, we have to add the kinetic energy plus the potential energy. But we can consider only the energy inside the box, because we only care really what happens inside the box. All our particles and our gas is inside the box. So really, we will say that the position of each particle is inside the box, inside this cursive V region of R3. So this just means that this is 0, okay, because we define the potential like that. And that the kinetic energy, well, is just given by this ultrarelativistic expression. So this will be our Hamiltonian. So really, what we have here is the Heaviside step function of E minus this sum. Sum going from n1 to n of C pi dq dt. Okay? So that's all we have for now. Now, before we keep on going, just remember that dq is dq1 and so on, dqn, where q, these vector q's are just the position of each particle in some arbitrary coordinate system, and dp is just the momentum. Now, notice that our Heaviside step function does not depend on the position. It doesn't depend on any q or r. Okay, so we can actually take it out of the integrals which are done with respect to q. So let me just write this a little more explicitly. And this integral can be expressed as the integral over p, okay, this is the phase space of the momenta, and the integral over the phase space of the position of our Heaviside step function. And for making things easier, I'll just write h, but just remember that this is h. dq dp. Now, remember, this does not depend on q. So it can come out of this first integral, and we will end with, let me just erase this. We will have the following. 1 over n factorial 3n, the integral over gamma p of our Heaviside step function, minus h, which only depends on p, let's just say p, times, well, or doing first the other integral, gamma q of nothing really, of 1 if you want, dq dp. So this is the same as doing first this integral and then this other integral. But what is this integral? We know that the integral over some region of space, say dq of 1 dq, is the volume of this region of space. And what is this region of space? This region of space is all the possible positions of our particles. Okay, we can rewrite this as follows. So it will be the integral, yes, it will actually be n integrals of q, no, let me just write it like this, v of 1, dq1, dq2, dqn. What this means is that this region of space, this high dimensional region, is nothing but the volume of our rocks n times, because the first particle can be in this region of space, v, but the second particle can also be in this region of space, and so on. So what we have really is that this gamma q is v, which is really just v raised to the nth power. Really, it's not, this is notation, this is not just really v raised to the nth power, but rather the union, right, of all these regions of space. But we know that in 3 dimensions, the integral over some region, let me just call it S, or, no, let's just call it V again, of 1 dq is just the volume, okay, in 3 dimensions. And what is the volume of this, right? What is the volume of this region? Well, we are given that this volume is just V. Okay, what this means is that we are measuring the volume of the space that particle Q, we just call it Qi, can occupy. As we said before, Qi can only be in the box V with volume V. So this is just V. If we keep on doing this for all the integrals, we will get V raised to the nth power. Okay? So the region of space that we have within this high-dimensional gamma of Q space is nothing but V raised to the nth power. But this is a constant in terms of P, so we can take it out of the integral. So let me just erase this. If this seems confusing, just it's okay, it's normal, it can seem confusing at first, but we'll be making videos on theory and many more exercises in which you can actually get the hang of it. So well, what this is just, let me just write it up here. Is just, well, our Gibbs factor, n factorial, or Planck's constant, 3n, times V raised to the nth power, because this can come out of the integral over P, times our integral over P of this. Yes. So this is what we have. Now, we said that, let me just draw this box again. We said that the particles with position R, okay, they have to be inside this box. But we have not said anything about the momentum. So even though the positions do belong in this region of R3, the momenta doesn't. So really, we can have that the momentum of the first particle, let me just say this, can go to positive infinity. Okay, this can go from 0 to positive infinity. So what we mean by this is that the set of all possible momenta is R3 times R3 and so on, R3, which is just R3n. What do we mean with this? What I mean with this is that the momenta, Pi, range between any value of R3. So we are integrating over this whole space. And let's see if we can see this clearer with some expansion of the notation. So the momenta has no restrictions, so we can have any value. This just means that this integral is done over R3, this one is done over R3, and this one is done over R3 of t, this function, dp1, dp2, dpn. Okay? So, once again, what I mean with this is that when we integrate with respect to P1, we're integrating over all of R3. When we integrate with respect to P2, we are also integrating with respect to R3, and so on. Well, really, I should have put this integral right here. So I should, sorry. What I should have done is this, but it's just a matter of observation. Okay, so this integral, this variable can have any value between in R3, this one also can have any value in R3, and so on, so on, so on. But how do we do this integral? Well, we have this little expression right here which can help us, and it tells us that the integral over R3n, right, if these variables can have any value, of the Heaviside step function of something, which is not exactly what we have here, is equal to 8 pi raised to the nth over 3n factorial. So how can we convert this expression into the one we have there? Well, let's just erase this and see how we can rewrite the Heaviside step function. So our function is this one. it is 1 if this holds, and it is 0 if this holds. Notice that because E is not 0, okay, we are assuming that the energy is not 0, we can divide by E in both of these expressions, so this inequality becomes 1 minus 1 over E, H greater or equal than 0. Okay, these two expressions are equivalent. But what is H? Well, we know that H is just the sum going from 1 to n of the speed of light times the absolute value of the momentum. And this should be greater or equal than 0. E is a constant, it does not depend on n, so we can distribute it to all the factors of the sum, leaving us with C over E. Let me just write this. So this is our new expression. Notice that it is similar to the one that we have in our cheat integral, but instead of the actual value of x, we have this. So let's just make a change of variables. So we will call xi, which I will call x1i, x2i, and x3i, this function. And we have that we want to make this change of variables. We want this to be equal to, okay? How will we keep on going from here? Well, this would be the same as saying that S1i is equal to C over E P1i, X2i is equal to C over E P2i, and X3i C over E P3i. So this is what we have. What is the modulus of this expression? Well, if we take the modulus on this side and this side, we have this, which is really nice for us because we can convert this expression into the one that we have here and use this integral. But we need to do something more because we're working in an integral, okay? So if pi can have any value in R3, well, this is just a constant. Really, xi can also have any value in R3. And now don't get confused, this is not a position, this is just some arbitrary function, vector function that I have defined just to make a change of variables. I could have just called it u, but I decided to call it x to agree with the integral we have there. So our integral, our gamma x, will be equal to gamma p. Okay, what I mean with this is it's just going to be 3n. The 3n dimensional real space. Now we have to take care of the differential, and this differential is just dp1, dp2, dpn. So in general, for any of the particles, we have that dxi is just dx1 I, dx2 I, and dx3 I. Okay, this vectorization, this vector differential is just notation to refer to the product of the differential of the three components. But what is this? Well, if you take differentials on both sides, we see that this is just C over E d P1I times C over E d P2I C over E d P3I. And this just translates into C over E to the third power of the Pi. And this is just notation for the product of the differentials of B. So, so far we have already made this change of variables. So let's plug it in and see how this works out. So we have b raised to the nth power, n factorial h to the 3nth power, and our integral, it is just to show the notation, I'm going to write 3n, and this is actually the phase space in X of our Heaviside function of 1 minus this expression, 1 going to n of C over E here. But notice that we said that this expression is equal to our new variable. So instead of this, we will actually just write this. And what are our differentials? Well, we said that this relation holds, so our dp or dpi is equal to e c to the first power dxi. So, but we have n terms, so we will have, let me just write it explicitly, e over c to the third power dx1 times e over c to the third power times dx2, so on, e to the c to the third power dxn. So really, we have n differentials, and likewise we have n e over c cubed terms. So let me just write here what we will have. So, just write an equal sign. We have volume raised to the nth power over f factorial, h raised to the 3nth power, and this integral right here. So I will just write it again. The integral over gamma x, which we know is just the 3n dimensional real space of our Heaviside step function, and this sum is over our new variable, and our differentials become, well, we have to multiply by this new term, e over c raised to the 3nth power. Yeah, remember, we have n cubed terms, so we have e over c raised to the 3nth power, and dx1, dx2, dxn. Just remember that each dx actually carries 3 differentials, so really here we have 3n differentials. But in our case, we don't care because we already know that this integral, which is exactly the one that we have here, is just equal to the expression. So we get that our volume is, well, v raised to the nth power n factorial h to the 3n times e over c raised to the 3nth power times this integral, which is just 8 pi raised to the nth power over 3n factorial. And this would be the expression of the volume of our phase space. So let me just erase all of this and write it up there, so we have it. And really, actually our problem is almost done. All we have to do now is some more tedious calculations to simplify the expression for the entropy. But we'll see now that they're not too bad. So let me just write this. Oh wait, and before we continue, let's just check that the dimensions are correct. So we have that the dimensions of V is, well, the volume is given in meters cubed. So let me just say meters cubed raised to the nth power. N factorial is just a number, it doesn't really have any units. H has units of action, so this is raised to the nth power. E has units of energy, joules, raised to the 3nth power. And C is just speed, right? It's a velocity, so it has units of meters per second, raised to the 3nth power. And all these are just constants. Remember that joules, well, we don't even need to remember what joules are equivalent in the SI unit. Just see that we have a J, S, and N to the 3n, N to the 3n. This is dimensionless. which is exactly what we wanted. We want it to be dimensionless. That's why we included this h factor. We could actually not include it, but in this case, it could not be dimensionless. Okay? So, let's just write this expression. Notice that we can take out a factor of n and rewrite this in a nicer way, right? 8 pi e cubed, really, v, all of this raised to the nth power, right? P v over n factorial, yeah, c. No, let me just do it like this. First of all, let's just write the 2 factorials here, n factorial and 3n factorial, and just all of this raised to the nth power. We have 8 pi e to the third power, the volume over ch, c cubed h cubed. So this is the volume of a phase space. So let me just check for a minute, and it is in fact the same expression that I have right here, isn't it? Yes. So well, that's that. Now we will get on to the entropy. And just before we continue, there are various definitions for the entropy, really. In our case, we're going to be using this one, where we have a Boltzmann constant times the natural log of our function, which depends on e, v, and n. But it could also be defined in some other ways. We'll see other problems with it, using the omega or W function, the increment in energy, or uncertainty in energy, or the microstates. But in our case, we'll use this one because it's I think it's easier and it's pretty straightforward. But really, it doesn't matter how we define the energy, because in the thermodynamic limit, all these definitions coincide. So that's it. We will just use this one instead today. So we have Boltzmann constant of, well, just remember that the natural log, we're working with real numbers, okay? So the natural log of A times B is the natural log of A plus the natural log of B. It's an important property, and it's really useful, and a really useful property. So in our case, let's just call this A and this B. And well, of course, we also have that 1 over A is the natural log, well, let me just call this A and B. Natural log of A minus the natural log of B. Okay, so in our case, we have this term multiplying this term. So we can add it, and also we have this relation. So when we partition this part, we can take out the n. Of n raised to 8 pi e cubed v, c cubed h cubed, and that's it. We can split this into the natural log of 1 over n factorial plus the natural log of 1 over 2n factorial, and using this property where a will be 1, we will get that this can be rewritten nicely as the natural log minus the natural log of this minus the natural log of 3n factorial. Oh, sorry. Of 3n factorial. Now, with that out of the way, we can use the Stirling approximation given by this. So we will now apply the assumption that we have a really large number of particles. Okay, right? We're working in the thermodynamic limit. And this will be, well, Stirling approximation in this case gives this, right, using this expression here. And in this other case, just gives the same, but replacing n with 3n. Okay, this is not 3 times n factorial, it is 3n factorial as a whole. okay, minus 3n plus n natural log of 8 pi e cubed over c cubed h cubed. Now, notice that we can take an n out of all the terms, so we will in fact do that. So this n goes away, this n becomes a 1, this n goes away, and this n doesn't go away, this one goes away, and this one goes away. Now, well, we can rewrite this as Boltzmann constant times n, and let me just think for a minute. Well, yeah, let's just keep it like this. Minus the natural log of n plus 1 minus 3 natural log of 3n plus 3 plus the natural log of 8 pi e cubed v over c cubed h cubed. Now, of course, 1 plus 3 is 4. Okay, so where do I write it? I'll just write it here. Okay, and this becomes approximation. So what we have is a kd, see how we can simplify this, times, well, we have to add up plus 4, okay, so this goes away. And now, we can put all the logarithms together. So this would go dividing here, this could come out on top as a third power, and this term would go down here. So we have that our final expression for the entropy is 8 pi e cubed v over n, okay, n goes dividing, 3n cubed, because we have taken this upwards, and c h cubed. And actually, because we have all of these terms cubed, we can just put them in here, and we end up with this. So this is our expression for the entropy. And there are two main things that we need to check when we do this. We can perfectly make some stately calculations, because there are a lot of calculations, and sometimes you can leave a number, a sign, or whatever. But there's something important that you have to do always, and that is to check the dimensions. So remember, the entropy that I wrote here has the same dimensions as the Boltzmann constant, and this is just joules per Kelvin. In our case, well, it has the dimensions of Boltzmann's constant, because this is dimensionless, 4 is dimensionless, and our natural log is dimensionless. Also, we need to check that it is extensive. So this is our first check. Our second check is that it is extensive. And, well, why don't we just check? So, if we place a lambda in front of all our variables, we get kv lambda n 4 plus natural log of, instead of writing, let's just do it. Well, let's just write this. Get this, and on the bottom you will get lambda n and another lambda here. So 3nch cubed. So lambda to the fourth power on top, lambda to the fourth power on the bottom. So these lambdas cancel out, which makes sense. And there's a lambda here. So this expression is the same as we expected. This lambda just comes out. So yeah, our entropy is extensive. And now the inside of the logarithm, well, it is just given by this. Is it dimensional to us? We have joules over joules times second over meters per second, meters cubed and meters cubed. You can check it yourself, but the argument of the logarithm is dimensionless. Now, we are really actually just finished with this. All we have to do is to compute some some quantities that, well, are almost trivial to do if you know how to differentiate. So let's just do it. So 1 over t is the partial derivative of s with respect to v when s is a function of e, v, and n. In our case, it is. So if we take the derivative with respect to e, we get kvn, and this is a really nice trick. All of this is constant, right? So we put, I'm going to write it like this. I'm going to write the natural log as this. But 3 dots and e cubed. Okay, because all these 3 dots don't depend on e. So we, by differentiating the natural log, we put 3 dots, e cubed, 3 dots, and take the derivative, 3 e squared. So these both cancel out really nicely. And we get that the temperature is 3n kV 1 over e. So let me just write this here. 1 over the temperature is 3n kV over e. Are the dimensions correct? Well, we have joules over Kelvin and joules. So we have joules over Kelvin over joules. This cancel out. And we have 1 over Kelvin, which is correct with our other side of the equation. Now, the pressure. Well, the pressure is just the temperature times the partial derivative of s with respect to v when it is a function of v, e, and n, just like before. So in this case, we will do exactly the same, but considering the volume instead. So we put 3 dots instead, the volume here, 3 dots, and the derivative of the volume with respect to the volume is just 1. So these two cancel out, and we get that the pressure is T kV n 1 over v. And we can rewrite this in a more familiar expression as PV equals to Boltzmann constant T n. This is the equation of state of a relativistic ideal gas. And as you see, it is the same as the equation of state of a classical ideal gas. We will do another exercise in which we will check this and prove it with a classical non-relativistic gas. Okay, so I decided to rewrite everything so the results are presented a bit clearer. And well, let's just get on with the last part of our problem. So all we have to do now is to calculate the heat capacity at constant volume and at constant pressure. Notice that here in our expression, the entropy is given in terms of Vn and T, but we have it in terms of Vn and E. So we have to express E in terms of T, and we already have it here when we computed the temperature. So first of all, we need to compute S, T, and V. Okay? So how do we do it? Well, we replace the energy for the expression which depends on N, V, and T. In this case, it only depends on N and T. So it's approximately, because of our Stirling approximation, given by Boltzmann constant times number of particles, 4 plus the natural log of 8 pi E cubed V 27 n to the 4th power H cubed C cubed, and that's it. So here, instead of writing the energy itself, we will write the expression in terms of the temperature, and it is given by 3 times Boltzmann constant times the number of particles times T. And well, this just cancels out with this one. This cancels out with 3 of them, with 3 with n cubed, and yeah, and we are left with this expression. We get Boltzmann constant and 4 plus the natural log of 8 pi kV T cubed volume n H cubed and C cubed. Now, in order to compute the heat capacity at constant volume, well, okay, let's just write it. T times the partial derivative with respect to T. So let's just do it. This is just this times, well, the 4 is constant, so it is 0, and we only have to do the partial derivative of the natural log. And if we rewrite it as we did before, we get this. And here on the bottom, it just goes the inside of our logarithm. But on the numerator, we need to take the derivative with respect to t. So instead of 3 of t cubed, we will get 3t squared. So our final capacity would be given by, well, t cancels out, and we just have, well, these two cancels out, and this is our expression. And really, this should be an approximation because we have used Stirling's formula, and the entropy is given in an approximate manner, not an exact. It's not an exact expression, but given the high number of particles, it's a huge number, so it is actually a really good approximation. So let's just write it. This is approximately 3 times Boltzmann constant and number of particles. Let me just write it better. So, well, we can do the same for the heat capacity at constant pressure, but in this case, we need the entropy given in terms of T, P, and N. So instead of having the volume, in this case, we need the pressure. So we need to find an expression for the volume, which is given in terms of T, N, and P. And we have it, and it is just the equation of state that we found before, the pressure, right? So let's just rewrite the entropy. We have KVN 4 plus the natural log of 8 pi Boltzmann constant T cubed, and instead of the volume, we write our expression. So let me just copy this. Okay. So instead of the volume, we write KV NT over P. So we have KV NT over P. And well, this just gives the following. The natural log of 8 pi Boltzmann constant squared T cubed, sorry, T to the 4th power, because we have another T here, and an N here which cancels out with this N, so that's it. And at the bottom we get P H cubed C cubed, and that's it. Did I make any mistakes? I think it is correct. So yeah, now what we have to do is to take the partial derivative with respect to a temperature once again. So let's just do it. We get Cp is equal to the temperature times, well, Kv N, and here we get our usual expression. Just write 3 dots, and the derivative of T to the 4th power is just 4T cubed, and on the bottom just get our usual expression. These 2 cancel out, these 4 cancel out, and we get 4 kVn. Okay, it's really similar to the other one, but instead of a 3, we have a 2. And just like before, this should be an approximation, given the fact that we're using Stirling's approximation. So let me just write it here. So the heat capacity at constant temperature, sorry, at constant pressure is 4 kVn. And really we have all we need. Let me just erase all of this, and we'll discuss the last thing of our problem, which is the ratio between the heat capacities. So this ratio is important in thermodynamics, and it is given by Cp over Cv. So in our case, Cp over Cv is given approximately by, well, 4/3. This holds for a relativistic monatomic ideal gas, which is the one that we're dealing with today. But in the case of a classical, that is a non-relativistic monatomic ideal gas, what we would get is, well, approximately 5/3. Okay, so instead of a 4, we'll get a 5. And we will actually see this in another problem in which really the setup will be exactly the same. We'll have a gas with some fixed energy, temperature, some fixed energy, volume, and number of particles. And in that case, the particles will not be relativistic. They will have some mass, and so we will have to apply another expression for the kinetic energy. So well, this is all for today. I hope you enjoyed the video, and well, see you in the next videos.